So today we're going to start lecture 8 with wrapping up and finishing the discussion of continuous variable observables with continuous spectrum. And we're going to start talking about the postulates of quantum mechanics. So it's going to set the stage for the rest of the course. All right. So in the previous lecture, we talked about the wave function. I'm going to review it, but at the same time, I'm also building a little bit more on top of it, right? Before I start, actually, are there any questions from the last lecture? All right, so here is Sakharai's notation. I repeat again. X is an operator. X prime is a number, right? So eigenket X prime. So this is the eigenvalue problem for X. And we said X has continuous spectrum. It's a Hermitian operator that corresponds to the position observable, measuring position. All right, we can take any ket and expand it in the eigenbasis of, whoa, what is this? In the eigenbasis of position. So this is just a resolution of identity that we set for continuous variables. It becomes an integral, right? And the ket prime, bra prime is a projection, but it's not normalizable. It's a Dirac delta function normalizable projection. All right. We gave this a name. We said that this is the wave function, right? This is the position wave function. This is the position space wave function of ket alpha. If you calculate the bracket of beta and alpha, you can do that by inserting a resolution of identity in the middle, and then you find that the bracket of beta and alpha becomes an integral over x prime of psi beta prime of x prime psi alpha. So now this should become clear, or at least it can connect with the function way of thinking about quantum mechanics you might have learned about in your undergrad courses, right? So when you talked about the overlap of wave functions, you just multiply psi prime with psi with psi star and psi 1 with psi 2 star and integrate it over the space, right? That's just nothing but inserting this resolution of identity inside this bracket to rewrite this bracket. Good? Is that clear? All right. So now one thing that you see is that these kets and bras are equivalent to the function representation of wave functions that you might have seen. For example, when I don't know if when you're in your undergrad courses, when you solve the Schrödinger equation, it was a partial differential equation for a function. So what is that function? It's a wave function. So we'll get there, but these are representing the same data, same information. It's just a reformulation using a more elegant notation that allows us to keep track of things more nicely, more compactly. All right, so this is the overlap of wave functions. Yeah, so now consider this quantity, which is the wave function of ket alpha in the position eigenbasis, right? So this guy is just this wave function. Now insert a resolution of identity for some observable, your favorite observable. I'm assuming for now that it has discrete spectrum. That's why I put a sum. Otherwise, I'll put an integral, right? So when you do that, what you obtain is you find the bracket of A prime and alpha that we gave this a name, CA prime, and then you find the bracket of X prime and A prime. So what is the bracket of X prime and A prime? If you were to give it a name, describe it. What does the bracket of X prime and A prime describe? So we said that this is the wave function corresponding to the state ket alpha in the position basis. this would be the wave function corresponding to the eigenkit A prime of observable A with eigenvalue A prime in the position basis, right? So what this tells you is that you could take any function, any wave function written in position basis, and expand it in terms of the eigenfunctions now of A prime in the position basis, right? And these are the corresponding coefficients. So this is an important step. Let's see. Are there any questions? Is this clear what I'm doing? Again, it should be clear that mathematically speaking, the trick I'm using is just resolution of identity. That is what I use to go from one picture to another picture. Any questions about this? Yes.
That seems a little weird. It's like you have state alpha, but it basis.
Yes. Let me here's you are familiar with this. Take a function on a circle. Function on a circle is written on a continuous as a function of an angle, which is a continuous variable. Now take this function and Fourier transform it. The Fourier transform on a circle is a discrete set of functions corresponding to the momentum. So you find a representation of a state which was first as in terms of a continuous variable, in terms of a sum over a bunch of discrete variables. It's the same phenomenon. So if you don't need quantum mechanics, I think that's a statement about mathematics. So you could think about that example. We'll see actually why Fourier transform. So yesterday, Tuesday, I made this cryptic comment, perhaps cryptic, that what I'm doing, all I did last time, which was defining the momentum operator as a generator of translations, right? As basically I said I'm basically going over Fourier transform. So today we make that clear. Why that's Fourier transform. Any other questions? So mathematically, this is really Fourier transform. But physically it's rich. Because we are putting layers of interpretations, right? Any other questions? All right. So now let's continue these tricks, and let's take the bracket of beta, some observable A, and kit alpha, right? Let's insert two resolutions of identity in the position basis, eigenbasis. So this is one, the other one is this. So what is the name of this guy? Can anyone tell me what this guy is? We'll just describe it. It's important. It's actually a good exercise when you write these expressions in your homework or reading the book. Find a term and try to say out loud, what does it represent? What is this thing, right? So x prime, A, x double prime is matrix elements of the observable A in the position eigenbasis. In the position basis. All right, so that's what this guy is. Now, what is x prime beta? It's star of it is x prime beta, right? That's the complex conjugate of x prime beta, which I said is the wave function corresponding to state beta in the position basis. So this manipulation hopefully is clear. But if you just go back to your quantum mechanics textbooks, wherever you learned it, you see these expressions written without this notation. If you did quantum mechanics before, and when you were solving Schrodinger equation, or you looked at hydrogen atom, it was all integrations, right? There were all sorts of integrations over space every single time, right? You wanted to calculate the expectation value of an observable, you had to integrate things. So this is the origin of integrations, right? The origin of integration is the fact that the position has a continuous spectrum. All right, let's work out a bunch of examples. So x hat and p hat are observables, right? Position and momentum. This means that any real function of position is also an observable. Why real function? Anyone? What is an observable? It's an operator that's Hermitian. If I take a function of position, which is not a real function, f of x will not be a Hermitian operator. All right, so take f of x to be Hermitian. It doesn't actually, for this analysis, it doesn't really matter. So you would insert two resolutions of identity, right? One here and one here, as I did here. And what you obtain is f of x prime, u of alpha x prime, u of beta x prime star. So, all right, how did I go down from two integrations over position to one integration over position? Dirac delta function. The Dirac delta function came from the fact that I had this expression. I had f of x and x double prime x prime. Forget about this. If f of x had x on this guy, what does it give me? It gives me f of x double prime. Why? Because this is an eigenstate of x hat. If this is an eigenstate of x hat, this is also an eigenstate of x, f of x hat. Is that clear or? Yeah.
This is an operator value.
Yes. Like x hat squared, x hat cubed, right? Or x hat plus x hat squared, right? Anyone want to just like tell me how to prove this? Yeah. Yes. Well, oh, sorry. You would Fourier transform. No, sorry, Fourier transform. You would Taylor expand this. You would Taylor expand this. Right? That's a very that's one way of defining f of x actually. So if yeah. All right, is this example clear? So now you can calculate the arbitrary matrix elements of f of x hat, position operator, or another operator in your favorite basis. All right, example number 2. So this example requires a little bit more attention. Recall what we talked about, the translation operator. We talked about the translation operator last time, this Cayley T of dx prime. We showed that this is nothing but 1. So this is an infinitesimal translation operator. This is 1 minus I p hat, which was momentum operator, d of x prime over h bar. I can't emphasize this enough. H bar had to be there, right? We argued for that, right? H bar must be there. You can't have quantum mechanics without H bar. It's absolutely required. And we saw that. All right. So this is take this as an operator. Now act with this infinitesimal translation operator on some ket alpha. We saw what this gives. This basically gives integral of dx prime, the shifted guy, x prime of alpha. We did this before as well, that because this integration was, we assumed from minus infinity to infinity, we could shift the domain of integration and change the variable by shifting the integrand, the variable we're integrating over, to rewrite it this way. This gives integral of dx prime x prime, the wave function of ket alpha at a shifted position. Now, this is just a function. I can Taylor expand it. So I get psi of alpha of x prime minus dx prime del x of alpha of x prime. As a result, the fact that the left-hand side has to be equal to the right-hand side will tell you, it will give you an expression for the action of the momentum operator written in terms of the X eigenbasis. What does it become? It becomes minus IH bar. Where do I get minus IH bar? From this side, right? I just bring this guy to the other side. So, yeah. Is this clear, or am I, is this from here to here clear, or should I write a line in between? Can you see how to go from here to here? Yes? No. Let me do it on the board. Actually, it's easier to do it here. So, what is the first term? I can rewrite the first term as, oops, ket alpha. Do you see why? Do you see why I can write the first term as ket alpha? Yeah, exactly. Psi of alpha of x prime, by now we've written it several times. It's just x prime, bracket of x prime and alpha. You get a resolution of identity, you just remove it. So now you have alpha on the left-hand side. This is 1 times alpha. Alpha on the right-hand side, you cancel them out. You have the action of p hat on alpha with a bunch of stuff equal to the right-hand side. You rearrange things and you find that the action of p over alpha is an integral of x, d of x prime, x prime, this expression. So in the position eigenbasis, you find the following equation, that the bracket of x prime p alpha is minus h bar, IH bar, derivative with respect to x prime. All right. A comment. So far, we've been talking about matrices. It's clear that matrix multiplication might not commute, right? It's clear that when I multiply matrices, they might not commute. What I'm asking here for is a representation of, so we know that we saw that, for example, delta of x and delta of y, they don't commute, right? So something delta z, I'll get minus sign wrong, right? Now, we also saw that we should have this, right? So the question is this: if I just represent in the x eigenbasis, right? So if I just put this in the x eigenbasis, this is just multiplication by x. P has to be something that does not commute with x. Derivative is exactly like that. Can you see why del x does not commute with x? What does it mean? Let's work this out. So you want to talk about this, right? So what is this? Let's say this acts on some function f. What would this mean? It means that first term is del x, xf. Second term is minus x del xf. Right? So this will give you 2 terms. Del xx will be 1, f minus x plus x del xf. These 2 terms cancel, you end up with f. So this expression is f, which means that the commutator of del x and x is non-zero, it's 1, as we wanted it. We want it to be something proportional to identity. So I wish somebody had told me this when I was taking quantum mechanics. This might seem magical, but the idea is that the same way that matrices have non-commutative stuff, functions and their derivatives also satisfy similar behavior. So functions and their derivatives basically generate a similar algebra in spirit. It's an infinite dimensional generalization of matrix algebras. But anyway, all right. So this, are there any questions about this step? Actually, let me go to the next step and then I'll pause. So this means that I could, using this trick, I could write down the matrix element of P in bracket beta alpha. I repeat the same trick by inserting resolution of identity. And once again, I find that this P basically in the position eigenbasis looks like this, minus IH bar del X prime. Right? So if I put minus IH bar here, I'm going to get minus IH bar. Right? So do you see now that the commutator of X, X and P is IH bar? Is it clear? All right. So this guy is the momentum operator acting on the position space operators as, or vectors as derivative wave function. Let me just write this wave function. Similarly, you could define P to the power of N, and that is differentiation N times, right? Is that clear? Any questions? I'm tempted to say a few more words about the connection between the two, but maybe I should pause for your question. If you're happy, I'm not going to say anything more. Okay. So now, based on what I've told you, tell me the following thing. What is the position space? What's the position space representation of this unitary operator, this operator? Tell me what's the position space representation is. Someone. So what is this? This is sum over n into infinity 1 over n factorial IAP to the power of n. What is the representation of this guy? Well, let me just put this here. IA to the power of n to the power of n. Anyone wants to say what this is? I literally have it on the slides. All you need to do is just look at the slides and say it loud. So I know it's early morning, so. So here, I and minus n. I and minus I will give you 1. That goes away. Actually, yeah, I wanted to do it. Let me put a minus. Well, it doesn't matter. I said what it said. H A del X. This is the representation of it. So everything you would do with operators, take a function of them, you could do with derivatives as well.
Yeah. Just replace
You don't have to. I just wanted to give you a cheat. I'm literally from the slides.
But we can just replace it there.
Literally, yes. But if you wish, the definition of this operator is this, so I'm just using the definition. But a fun fact is this: if you act with this and some psi of x, what do you get? What does this operator do? We talked about this in the last lecture. What does this operator do? What does momentum operator do in the position basis? Translation. It generates this translation. This is the operator last time I called a finite translation. At the end of the last lecture, we derived this, that this is a finite translation. Now, it's easy to see why. Take this guy and act on psi of x. Maybe you can't see it. All right. Just you could do algebra. Right? This is just Taylor expansion. This acting on psi of x will will shift x. Oh, sorry. No, that's all right. Spread a bit further. We'll shift x by how much? AH bar. All right. Any questions? Am I going fast? Slow? Yes. Yeah, this variable?
Yeah.
Yeah, it's just a number.
So it's not how packets. You can translate anything.
Yes. This is completely continuous, even though there is an H bar in it, but everything is completely continuous. Yeah, everything. So this is the X and P are not quantized observable the same way that sigma X and sigma Y are. They're not, they don't have quantized, they have continuous spectrum. The H bar controls the finite resolution of the phase space. The fact that we had the uncertainty relations, that we said that you can't know the answer to the position, you can't measure the position and the momentum with arbitrary resolution. So there is an H bar that controls that, but here everything is continuous. It's completely, all variables are continuous. Did I address your question?
also
Light? Oh, we'll get there, but yeah, yes. So if you, yes, in photonics, that's what, it's a continuous variable. Not, there's one subtlety that I'm not willing to, yeah. Sort of, yeah.
But are we assuming a small?
So, oh, very good. Does anyone have an answer for that? What are we assuming that's small?
Finite translation.
Yeah, the translation is small. But do we need to assume that? It's a question of domain of convergence. Oh, maybe this is too math for you guys. But yeah, just assume it's small. Yeah, this whole thing is small. Another way of saying is that, yeah, the eigen operator, the eigenvalues of this observable are small. Why do I say this observable and don't say P? Does anyone know why? This is an extremely important lesson for physicists. Never say the eigenvalues of P are small. That's nonsensical, completely nonsensical. But AP, the eigenvalues being small is sensible. Does anyone know why? Is 1 meter large or small? There's no meaning to 1 meter being large or small. Only numbers could be small or large. Dimensional quantities are absolutely meaningless to call them large or small. It depends on your unit, right? A meter, if I use like my ruler or like mark with nanometers, is gigantic, right? So a dimension full parameter makes absolutely no sense to talk about it being small or large. Never ever say that. If you ever say that, people will make judgments. But this is a dimensionless parameter. A number can be large or small. Good? Is that clear? Very, very important. Based on what I just told you, when you take function of something, f of x, and expand it, it doesn't make sense to say that x is small, right? But or another way of saying that is that e to the power of I something. The only way to exponentiate something is that the thing you could exponentiate has to be dimensionless, right? Always, dimensional analysis is your friend. You could save so much time and avoid so much headache if you just pay attention to the dimensional in the problem, right? Is that clear? So that was everything we said was about the position space wave functions. How am I doing on time? Okay. All right. Everything I said was about the position space wave functions. Now let's talk about momentum space wave functions. So momentum space, these are kets, eigenkets. The eigenkets, the momentum operator is an observable. They span the Hilbert space. They have this orthonormality relation, quote unquote, because it's Dirac delta function normalizable. Orthogonality, perhaps, is a better word for it. Now, if you take a ket alpha and insert the resolution of identity this time in the momentum eigenbasis, I'm just repeating the previous analysis, replacing x prime with p prime, right? I get the integral of dp prime, the momentum space wave function, right? So now the question comes up. If I have a ket alpha, I can write it. Well, actually, let me write it down here. Let me write it on the board. If I have a ket alpha, we wrote it as, we expanded it in the position eigenbasis, or we could expand it in the momentum eigenbasis. This is another. Same ket, right? So your state is not a wave function position space. Your state is the ket. This is a representation of the state from the point of view of the observable x prime, x. This is the representation of the same state from the point of view of another observable. Good. If you recall, we made this statement that every time I have a pair of observables, there was a theorem. Their eigenbases are related by a unitary that we call this a change of perspective. So here are two observables. What's the unitary that relates the two? Well, actually, you already know what it was. Well, okay, let me not go. But the answer, let me give you colloquially the answer. Fourier transform. Yes. So we're going to see that. If you recall, the proof of that, the theorem I was coding was I had two operators, A and B. This had eigenkets A, and this had eigenkets B. I took one eigenket here and expanded it in terms of the other one, right? So here is precisely what I'm doing. I take the eigenket X and insert the resolution of identity for P prime in there. Now, this is the transformation function. Okay, so what is bracket P prime X prime? That's what we want to calculate. If I tell you what bracket P prime X prime is, I've told you how to go in between the two pictures. There's a simple way to calculate this. So take the P operator and put it in the middle of a bracket X prime P prime. When P acts on P prime, it will give you P prime, oops, it will give you P prime bracket X prime P prime. But this is a Hermitian operator, so I could alternatively act with it on this guy. That will give me minus IH bar del X prime of the same guy. So now I have a differential equation, right? P prime of X prime P prime is minus IH bar del X prime of the same thing. If I integrate that, I just get this bracket is some constant exponential of I P prime X prime over H bar. Why is there constant there? It's the first order differential equation. There's a normalization, so I have to fix the normalization. That's my next step. Good. To fix the normalization, I noticed that my bracket of X prime X double prime is the Dirac delta function. All right, so let's stick a resolution of identity. That tells me that, well, this guy, but which one did I calculate? P prime X prime. No, I calculated X prime P prime. So X prime P prime is this object. This is the composite conjugate of it with X prime replaced with X double prime. So these two guys give me this exponent, and each of them will carry a function, an n. This is n squared. Is that clear? Now I can normalize things because this has to be a Dirac delta function. I can do this integral explicitly. Do you guys know this integral? E to the power of d of x what is this integral? From minus infinity to infinity. Yes. It's a Fourier transform of what function? One. What is the Fourier transform of that function? Dirac delta. So if you were wondering where the hell Dirac delta function came from, how mathematicians invented this guy, it came out of the desire to talk about Fourier transform for an extended set of functions. What's the Fourier transform of a Gaussian? Gaussian. So, and here, accept this as a fact, I'm telling you a fact. If you have a function, so Gaussians fall at infinity, right? When you Fourier transform them, the Fourier transform falls at infinity as well. If you have functions that don't fall at infinity, or maybe fall a little bit too slowly at infinity, they're not square integrable, then your Fourier transform will not end up being a function. It will be something like a distribution, like Dirac delta function. So Dirac delta function was invented in mathematics based on the desire to extend Fourier transform to things, to functions that like constant functions. Literally, not like, but exactly constant. All right, so here it is. Putting everything together, we find that the transformation function, bracket of x prime p prime, is exponential ei px prime x prime over h bar, 1 over 2 pi h bar. All right, so I will not. Any questions? This is a very, very deep result. I can't stress this. Because I was gonna say something, but because people said the face space is not very familiar to them. This is the essence of quantization of face space. I just told you that everything you see inside an exponent, if you write exponential of a bracket, the thing that's in there must be a number, right? So what is the dimensionality of h bar? Same as x times p, angular momentum, right? Any questions? I'm pushing some stuff under the rug. I'm wondering if somebody's going to give me a hard time. So far, I'm getting good. Yeah.
Sometimes it's just taking like
It's taken as?
like sometimes this is there's a order inverse transform equation.
Oh, you're asking whether it's inverse Fourier transform is the Fourier transform? Yeah, I'm always going to get that wrong. I apologize. For me, it's like which one you pick to be the Fourier transform, the other one is the inverse, is your choice. Actually, there's another important choice that I'll always confuse you guys with. So when you Fourier transform, sometimes people split the 1 over square root 2 pi. Sometimes they put 1 over 2 pi here, 1 here. Sometimes the other way around. I can assure you, I'll confuse everybody with this. Because with two calculations, I never follow the same dimension. As long as you set the, because you know the 2 pi. Yeah, it's just like you make that choice. Once you work with these Fourier transforms enough, you learn how to use them efficiently, right? It's a little bit like you want to do a calculation with matrices. You start doing the calculation, you pick a notation. You realize that, oh, you're dealing with too many indices, like Dirac. And then you said, well, or Einstein. And then you said, oh, I'm just not going to write the sums. Every time the indices repeat, I'm just going to assume that's a sum, right? So I invented this notation. That's simplified. All right. Any other questions? But now there's something else that I've also told you. This whole business from the last lecture, position and momentum, uncertainty relation, everything I've said, there was nothing specific to X and P about it. All that it took was an observable with continuous variable, continuous spectrum. So everything I've said could be generalized to that setup. To, if you know classical mechanics, general, well, we call generalization of X is called generalized coordinates. And the generalization of P is called corresponding conjugate momentum. And we satisfy these relations. Everything is identical. Everything. Yeah.
Was the thing body both sides by the graphical to zero value?
No. No. The thing that
why are we allowed to do that? Because it's zero value.
Which one? Sorry.
The direct delta, you divide by both sides.
I just canceled them. Yeah. These manipulations are kosher. They're okay. I can explain why, but I'll do that after the class. The thing that I was hiding under the right that no one complained about is that I said it only makes sense to write things that are dimensionless, and I just immediately violated that. Can you tell where I violated that? All right, I leave it for you guys to decide. If you still can't see it, it's all right. You can no longer see it. All right, good. So now what do we find? We find that writing psi alpha of x prime, which was, I'm just thinking loud, the wave function, position space wave function corresponding to the ket alpha, could be written as in terms of the wave function representation of the same ket in momentum space, and the transformation is literally Fourier transform. All right, let me comment on this. I can't do this. So what's the dimensionality of H bar? Does it make sense to take square root of angular momentum? No. So I'm hiding a dimension full parameter here. Can anyone see where I'm hiding it? Does it make sense to integrate the dimension full parameter? No. Think about this stuff. Yeah. All right. Good. All right, good. So what we found in summary is that we found that the position space wave function and the momentum space wave function for the same ket are the Fourier transform of each other, right? So if I say they're the Fourier transform of each other, I don't need to clarify which one is Fourier transform and which one is the inverse. Okay. Now, one more thing that I have to say before talking about the axioms of quantum mechanics. Gaussian wave packets. So in physics, we often want to talk about things that are Gaussian. Do you know why? They're natural in nature. They're just very, very natural. If you don't know anything about the state, it's a fair assumption to take it to be Gaussian. If you don't want to know, and this is a scientific best guess. If you want to know why, you could take a course on inference, but it's basically law of large numbers. So Gaussians are good guesses. If somebody comes to you and says that, like, I did some statistics and my sample was 1 million people and there was some result that they found. Guess what the result is? You know absolutely nothing about the result. The fair guess is the Gaussian, right? All right. So what's a Gaussian? What's a Gaussian wave packet? It's a wave function. So take a ket alpha. If you take this, write this ket in the position eigenbasis, it's a Gaussian wave packet if it takes the following form, which is a Gaussian multiplied by phase normalized properly. So this normalization is to make sure that the wave function square integrated gives you 1, right? This is a phase because this guy is, I'm allowed to have a phase, right? And hopefully it's clear that the normalization does not depend on K, the phase. That should be also clear. What's the meaning of D? What does D control? So look at that. Exponential of I K X prime. K X prime must be dimensionless. Good. Minus X prime 2 over 2D squared. D squared should have the same, D should have the same dimension as X prime. So D, before knowing what it is definitely some sort of a length scale. And this is your function. It's a length scale that tells you about the width of this, right? How pointed the distribution is. It's just a width. You can see all of this by dimensional analysis. All right. So assume that this is the wave, this wave packet is the wave function. It describes the wave function of a particle with this, and the wave function squared is the probability density of the particle being at some point, and that takes it Gaussian form, right? Is it clear that that's a square that square that? Just drop the figure square the rest, right? It's also, I chose it to be centered at the origin. How would I change this guy if I wanted to not be centered at origin? How would I change it if I want to be centered at X prime 0? I would just take this X prime squared and write it as X prime minus X prime 0 squared. Good? All right. So that's the Gaussian wave packet. Yeah. At this point, it's just a name. Almost take it as a definition. I'm allowed to put a phase there, and I'm gonna put a phase there, right? And I just use a suggestive notation K, and I gave you the suggestive name. At this point, there's no very good question. Yeah, if it seems like I'm taking a leap or something, ask. Sometimes I hide things, but not always. Questions? No, we did not ignore it. We took the norm. So this it cancels, right? Well, it gives you one. The phases give you one. All right. So a bunch of tricks. Well, I'll do these calculations, right? I'll do them quickly. So your ket is that alpha, right? It's a wave packet. If you have a wave packet of that form, if you calculate the expectation value of x in this state, now you know how to do it using the integrations and the rules that I was describing earlier, right? You just do it step by step. It becomes the integral over the Gaussian multiplied by x prime. What is that? That gives you the peak of the Gaussian, which I chose to be 0. So it gives you 0. But just do the integral for yourself. It's pretty straightforward. And I encourage you to do the integral by hand and not using Mathematica at least 10 times. Because there are times in Mathematica when things get wrong. It's important. All right, so that's x. This is x squared. Let's calculate x squared. X squared will give you basically the integration of the x prime squared with the same kernel, right? The Gaussian kernel. And that gives you d squared over 2, right? That's the meaning to that. That's why d characterizes the width of the distribution. All right. So now let's suggestively calculate the variance. You can tell where I'm going with this. So that's x squared minus x expectation value squared, which is d squared over 2. Good. So what was the Fourier transform of a Gaussian? A Gaussian. I could literally repeat this analysis replacing p x for p. And I'll find similar expressions for delta xp squared. That's what I'm going to do next. All right. Similarly, you can do it the way that I just described, or what you could do is that you could calculate the expectation value of p in the position eigenbasis. I recommend doing both. In the position eigenbasis, if you're calculating, what should you do? You should integrate over x with the Gaussian wave function e to the power of I kx blah blah blah. The representation of momentum operator in the position space, which is a derivative, acting on the second time, right? So that line, let me skip the first line. Let me schematically write it. But these are things that. So that the first line looks like this. So it will be 1 over n squared integral of d of x e to the power of I kx x squared minus 2d2. I'm gonna copy the second one here. Oops. I kx minus x squared over 2d. I have to put the representation of the momentum operator in the position eigenbasis. What was it? Minus I h bar del x prime. Yeah, x. All right, you do this integral, you're going to get 0. Oh, sorry. You're going to get h bar k. You're going to get h bar k. Why? The Fourier transform of a Gaussian, the way I defined it, is a Gaussian. But if the first one was centered around the origin, the second one need not be centered around the origin. It would be centered around the origin if I didn't put that e to the power of I kx. That's just Fourier transform, right? But it is important that you build intuitions. You know, like You go through Fourier transform, now there's a layer of physics interpretation. You see what's happening. All right, so very good. You calculate p squared as well. Work these out for yourself. You multiply them, you obtain, so this time around, you get h bar over 2d squared. When you multiply these two, you're going to get h bar squared over 4. Does this satisfy the uncertainty relations? Yes, but it does even better. It saturates it. So Gaussians are the wave functions with minimum uncertainty. You can never do better than Gaussians. That finite resolution of nature I was talking about, if you want to work that at that ultimate resolution, you will be working with these Gaussians. You could also write down the wave function and the momentum eigenbasis of the same ket. This is the expression for it. And you see explicitly that the previous one was centered around the origin at x, and this is centered around h bar k. Right? I just did Fourier transform. Sorry? Relation, sorry. The saturated minimum wave uncertainty wave packets. Sorry about that. Now, D was a measure of the width of the D was a measure of the width of the wave packet in the position eigenbasis. When D goes to 0, it means what? It means that you have no uncertainty in position eigenbasis. It becomes a Dirac delta function. You know exactly what is going on. What happens to this wave function when D goes to 0? It becomes 1. You have no clue where the momentum is. The wave function of the momentum becomes a constant. Right? That's terrible. So if you minimize one, the other one, if you know one absolutely perfectly well, the other one you don't know anything about. Good. All right. And there's of course a compromise between the two. There's a if you make one of them peak, the other one will be y because of uncertainty relations. I'm tempted to. I'm also hiding something under the rug here as well. I'm wondering if somebody sees that, but not when I hide something. It's not that I'm lying to you. I just don't want to expose you to all the complications at once, right? I could be doing this rigorously, teaching you L2 spaces, but I'm not. Any other questions? All right. So the generalization to higher dimensions is straightforward. It basically becomes is very similar. We said that the X operator is the X elements commute. So there's an X vector operator. There's a P momentum vector operator. The inner products of their bases will be a Dirac delta function, but now it's delta 3 dimensions, which is the multiplication of the x and y and z, because these are independent operators. All right, the rest goes for the right. Everything is as usual. The integrals are now d3 of x, d3 of p. And the expressions for wave functions are analogous. I'm going to go to the next step. These are pretty straightforward, but if you have questions later, ask. All right, so now there's a pause. Are there any questions? Because I'm going to change gears. So we're approaching the end of part 1 of the course. So far, I've been walking you through a bunch of notations and trying to justify the results, build a mathematical formalism to describe this observable, these two measurements, Stern-Gerlach and the double slit experiment. So Stern-Gerlach motivated the discrete case. I could have motivated the continuous case using double slit, but we just didn't have the time to do that, right? We could do the exact analogous. I just said, imagine X and X has continuous spectrum, right? I could have just forgotten that, started the course using double slit, using X and P, right? So that's an analogy between the two experiments. Now, what are we going to do? Now you know enough about it that you could take a step back and think about what the hell is quantum mechanics. So we have to abandon our very nature of classical physics and reality as we know it. We have to make postulates, right? So I'm going to go over 4 postulates of quantum mechanics, right? And you will see this will actually lay the foundation of the course. There are 4 postulates. The first one is basically what you've seen already, sort of, with some subtlety. First one says the following. It's the postulates of states and observables. This is what everything we've gone over so far. It says associated to every isolated, that's the key word, it's important, physical systems. All the systems you're talking about were isolated. They were not at finite temperature or interacting with the environment. Associated to any isolated physical system is a complex vector space with inner product called a Hilbert space, right? We went over that. Known as the state space of the system. The system is completely described by a state vector, a ket. A unit vector, we said it's a unit vector, right? The normalization had no physical meaning in the state space. Also, every measurable physical quantity, aka observable, is described by Hermitian operators. So this postulate we've gone over. There is a subtlety here. That's the word isolated. We'll come back to that later, maybe next lecture, actually. You could remove the word isolated and write the 4 postulates of quantum mechanics again, and I'll try to do that next time. So, all right, so this so far you have seen, and this summarizes part 1 of the course, right? So what is the rest of the course about? It's about the other postulates. Is that clear? Good? All right, postulate 2. You have also seen this one, more or less, and you haven't seen it completely, but we're not going to play around with this postulate too much. It's a measurement postulate. It says when observable A is measured in some state, which now is a ket psi, the probability of finding an eigenvalue A prime is P of A prime is that guy. We went over that, right? The component of the vector, the normal the component of the vector. And after the measurement, the state is thrown to the corresponding eigenvalue. I realized that to match Sakurai's notation. No, actually, yeah, let me match Sakurai's notation. This is bad. This is bad. All right. Sorry about that. I want to make sure that you guys don't have to think too much about the change of notation. All right, so now that's Sakurai's notation. Good. So far so good. And then if there are degeneracies, which is when a ket A prime has the sorry. Well, I try to oversimplify it. When there are degeneracies, this would be we cannot use the notation of A prime anymore. We'll have to have another constant that counts the degenerate eigenstates, right? So if this is like, for example, G A prime degenerate, you'll have a sum correspondingly. right? So this postulate you've seen before. Let me move this guy. Good. Questions? All right. Now, in the remaining 7 minutes or so, I want to tell you about the other two postulates, which are going to be the part 2 and part 3 of the course. Right? The second postulate is the evolution postulate that describes dynamics. We haven't said a single word about dynamics so far. It says the evolution of a closed quantum system is described by a unitary transformation. We have introduced unitaries, so now you know what the statement says. That says that if you have the kit at some time t1, and you want to know the kit at some time t2, there will be a unitary that's labeled by t1 and t2 that will relate the two. Recall what a unitary was. It's an operator u such that u dagger is equal to u dagger u equals identity. Good? Yeah. Closed, yeah. So the red word closed is related to isolated. Not interacting with an environment or not at high temperature. So I'll come back and write the postulates next lecture more general. Good? Now, all of these are very, very deep postulates. Of course, it's a postulate. The fourth one is perhaps the one that was underappreciated for a very, very, very long time. And I would say it's fair to say that even to this day, this postulate is like under development. It's a postulate of composite systems. It says the Hilbert space of composite systems, now you know what the Hilbert space is, right? Is the tensor product of the Hilbert space of each component. So I haven't told you what tensor product is. We're gonna go over that in part 3 of the course, but I wanna tell you in advance. It tells you how to describe systems that are composite, have multiple components, multiple particles. I was just talking about the wave function of a particle on a line. What about the wave function of 2 particles? And how to formulate that, right? So that is going to be postulate 4. Good? And these are literally going section by section over the course. Section 1, we are finishing it, was about the first 2. Section 2 is about, or part 2 is about postulate 3. Part 3 is about postulate 4. Now, postulate 4 of the course, part 4 of the course, we're gonna, so part 3, we're done with the postulates. Part 4 of the course, where I'm gonna tell you a little bit more about, this is not postulates of quantum mechanics, but more nuances in physics. We're gonna go over symmetries, charges, and their mathematical formulation of direct sums of Hilbert spaces. So the analogy I wanted to draw is given 2 vector spaces, right? Linear vector spaces. There are 2 operations mathematically I could do. I could direct sum them, we'll define that. I could tensor product them. If I tensor product them, the postulate, so that's a mathematical operation, but postulate 4 tells you that what you're doing is that you're describing a composite system. There was a first Hilbert space described particle 1, second Hilbert space described particle 2, and now you're describing 2 particles, right? The other operation you could do to Hilbert spaces is direct sum. Something is pretty simple. We'll go over it, and that's going to be part 4 of the course. If you do that, if you take the Hilbert space of 1 particle and direct sum with the Hilbert space of another particle, you're not describing 2 particles. You're not describing 2 particles. You're talking about a system with conserved charges, and we're going to go over that. Right? So that's the rest of the course that we're going to cover. Are there any questions? Yes. You don't need Schrödinger equation for quantum mechanics.
How do you know what determines
What is the Schrödinger equation? equation? Does anyone know what the Schrodinger equation is? What's the left-hand side of Schrodinger equation? Yeah, so I dt gets psi. So I told you what psi t2 is. Take a derivative from the left-hand side. The right-hand side, you have to take a derivative. Hamiltonian is the derivative of the right-hand side. The definition. So, but you don't need to say those words. This is actually a little bit more. I can tell you a little bit more about it. We will get there. Actually, yeah, we'll discuss this in detail. All the nuances of why I don't necessarily say Hamiltonian at this point. There are some subtleties. It's not as simple as this. All right. Any other questions? So let me summarize. And yeah, that's actually the rest of the course. And that's my goal. Along the way, oh, sorry, I forgot to say, there's part 5 of the course. Is there part 5? Yeah, no. So when we go part 3 of the course, when we go over composite systems, that is something that's not in Sakurai. That's not a chapter of Sakurai. So we're going to go off script. And I'm going to teach you guys what entanglement is and all of that, right? This is all hidden in part 4. So in summary, what did we go over today? We talked about the going in between pictures for a wave function, for a ket alpha, describing it in the position eigenbasis as the wave function of ket alpha and position eigenbasis, or wave function of ket alpha and momentum eigenbasis, and we saw that they're related using Fourier transform. We said that the representation of the x operator in the x eigenbasis is just multiplication by x, whereas the representation of p operator in the x eigenbasis is minus IH bar derivative with respect to x. And repeat everything what I said, switching x and p. Right? P in the position eigenbasis is just multiplication by p. P in the x in the position eigenbasis is actually I over h bar del p. Over h bar. Okay. Any last questions? If not, thank you so much, guys, and I'll post homework number 2 today.